Great. Thanks a lot for the introduction, and thanks a lot for inviting me to this great workshop. So this is work that I'm presenting, but it was really led by Maxime Gass and Didier Schittler, with help from Nicolas Ferroni and advice from Andrea Lodi. And myself. I should also say this is, if you were at Vinod's talk earlier, the first talk of the day, this is really sort of a prequel to that talk in terms of when the work appeared. And so I think lots of the concepts, I'll reuse lots of the concept that Vinod talked about, and hopefully I can get into some more details in some of these. Okay, so the goal here is to solve combinatorial optimization problems. And we know that solvers exist. Sort of commercial grade solvers exist that can provide exact solution to such problems. The use case we consider here is that we're in a setting where we want to regularly solve problems from the same family. Okay, so imagine that every day you have to solve a slightly different instance of a TSP problem. Of course, this sort of use case is interesting for machine learning because you can imagine that you may be able to collect historical data, train with that data, and then use your machine learning heuristic to help the solver solve new problems faster. Okay, and so really what we're trying to do here is we're trying to use machine learning as a heuristic inside the combinatorial optimization solver. So this is the image you can have in your head, is that you have the solver, which takes in as a problem, and once in a while, it will give its state to the machine learning model, and the machine learning model makes a decision and gives it back to the solver. At the end of the day, you get a solution. So there's many different decisions we can make inside the solver, as I'll talk about later. The one we focus on in this work is the problem of branching. So a quick overview of my talk. I'll first introduce branch and bound and branching. Then I'll talk about machine learning modeling, how we can model this as a sequential decision-making process. Our contribution here was to introduce GCNNs, graphical convolutional neural networks, for this task. And then I'll end with a numerical study. So introduction to branching. So the sort of combinatorial optimization problem we're talking about can be cast as a mixed integer linear program where you're trying to minimize an objective function where you have variables x according to a set of constraints. You have lower and upper bound constraint on x's, and in particular, it's an integer program because a subset of the variables need to respect an integrality constraint. Okay, so in general, this is an NP hard problem, and while we have solvers that can solve lots of sort of small scale instances, in general, it's still very hard to solve larger scale instances. Okay. So one thing you could try to do, one thing we know how to solve are LPs. And so if you relax the integrality constraints, if you remove the integrality constraints, you obtain this linear program. And of course, this linear program is much easier to solve. It's convex, and we have efficient algorithms to solve it, such as the simplex. So now, of course, you'd like to relate these two things, the LP to the MILP that you had earlier. So there's a few things you could say. So first, if the solution to this LP, which I call here X star, obeys the original integrality constraints, then you're lucky, right? And you effectively found a solution to the original MILP. I can say this will depend a lot often on the type of constraints that you have. And in fact, if you've ever submitted a paper to a conference, to a computer science conference, this paper was reviewed. And so effectively there was this assignment process, this MILP was solved. And it turns out that for this particular MILP, you can actually solve it as an LP and obtain integral solutions. Okay, but this is sort of where we're lucky. And so if you're lucky, you're gonna get this. Most of the time though, you can imagine you're not gonna be lucky. That is, at least one or more of these integrality constraints are not going to be met, or the solution is not going to obey these integrality constraints. But at least you get a lower bound, right? You've solved a relaxed problem, and so you get a lower bound of your original method. So now this idea of getting bound on this MILP is exactly what the branch and bound algorithm does. The branch and bound algorithm is so the vanilla algorithm that is used, I believe, in all combinatorial optimization solvers or all MILP solvers. The basic idea of branch and bound is to split the LP recursively over a non-integral variable. So imagine that in the LP solution, you have x star and xi star rather is a non-integral variable. Then you would split your LP into two LPs, and each one of these sub-LPs has one added constraint, right? So you've effectively split the search space. Okay, and the constraints are as such. So you take a fractional variable, and this floor, or the integer value will be an upper bound for your xi, and similarly similar for the other LP. So you can think of this as creating a branch and bound search tree where each node here corresponds to a MILP or to its relaxed version to an LP. And then when you go down the tree, you're effectively adding nodes. You're pruning your search space. So the further down you go, the easier the problem gets, or at least the smaller the problem gets. So we've already talked about lower bounds. You can think of, if you look at all the leaf nodes, you can think that the lower bound to the original MILP will simply be the minimum objective value amongst all the leaf nodes. It turns out you can also get an upper bound, right? So whenever you solve an LP, wherever you are in the tree, and it returns an integral solution, then you know that you've actually found an upper bound to your original problem. And it's an upper bound because it's integral, right? But because you've added constraint, the search space is actually smaller. So in general, it'll be an upper bound to your initial problem. Branch and bound proceeds by creating this tree and searching in it. And it stops when one of these three criterion is met. Either you found an optimal solution, so the lower bound is equal to the upper bound. Either when you're solving the original LP, you realize that there's no relaxed solution. And so in fact, the original problem is infeasible. Either you may want to stop when you're close enough to, when you're, say, 1% away from the optimal solution. So this is what this L minus U smaller than threshold means. Okay, so I won't talk more about branch and bound, but what's important to note here is that this is really a sort of sequential decision process through time, right? You're searching and expanding this tree through time, okay? And it's a sequential decision process, but at each step, you can make multiple decisions. You can make a decision about which variable to branch on, right? So if I go back, xi here is the variable I'm branching on. That's what we care about in this paper. There's also node selection, right? Do you want to jump in the tree? And there's all sorts of other decisions that modern solvers can take. Basically, state-of-the-art solvers, state-of-the-art and branch and bound solvers uses expert rules. So for each of these decisions, you have a particular heuristic, and often lots of heuristics are being combined all together. But what's maybe interesting to think about is that there's not necessarily a clear objective or a clear consensus on the objective that we should be using, right? Of course, you can think of, you want to find the optimal solution as quickly as possible, right? So L might be equal to U, maybe that's what you want, but perhaps you want something else, like you want this duality gap, right? Basically the space between the two to reduce as fast as possible, right? Or you want to get to the 1% optimal gap as quickly as possible. And in other problems, you may care about different things, right? So in some problems, you may care about finding really good dual bounds or finding really good upper bounds, primary bounds, okay? Okay, so in terms of branching, because this is what we care about here, there are basically these three expert rules that can be used. Of course, there are others. I guess I should say I'm going to talk about these three. First, there's strong branching. Strong branching, what it does is at each node, for each candidate variable, it will split the variable and it will solve each resulting LP. okay? And then it will pick the variable, it will branch on the variable that results in a Titus relaxation. So basically what you can imagine, this is spending a lot of time on each node, solving two LPs for each candidate variable. And so this will lead to very small trees, but it's also very computationally expensive. On the other end of the spectrum, you have pseudocost. Pseudocost is backward looking. It basically keeps tracks of how good was it to branch on a particular variable, and then it will pick the variable that is the most promising variable given what has happened so far. So this is very fast, but of course it could suffer from the cold start setting, whereas at the top of the tree, your prior over variables may not be very good, right? It could be, for example, it could just be uniform. And then there's something in between, which is called reliably pseudocost, which is sort of the best of both worlds. At the top of the tree, it's going to use strong branching to predict decisions, or to predict variables to branch on, and then it's going to gradually switch over to pseudocost. And I think this is, in terms of a heuristic for branching, this is the best overall solving time trade-off on MIPLET. Okay, so this was sort of it for the very quick introduction to branch and bound and branching. Now we're going to talk a little bit about machine learning modeling. So we said that branch and bound was a sequential decision-making process, right? And so the go-to tool we have in machine learning to model such problems is an MDP. In an MDP, you have an agent that's interacting in an environment. The agent makes action. The environment responds with a new state. And the objective of the agent is to maximize the long-term reward, or the discounted sum of the long-term rewards, right? Where R here is your reward function. We can think of MDPs for branching as such. So the environment is the solver, and so the state of the solver is the state of the environment. The action, it's which variable to branch on. In the general case, you can branch on any of the variable with integrality constraint. And then you can think of a trajectory or an episode as solving a single MILP instance. So at time 0, you have your initial state S0 is just the current, the MILP, the initial MILP. And then at time capital T, or at state S of time capital T, the MILP is solved. Oh God, look at this. And then in between, right, how you sort of move from one state to another depends on two things. It depends on the branching policy, right? So which variable do you decide to branch on, and it depends on the internal of the solvers, which will rely on your branching decision, right? So you have effectively an expectation over the next state. And so you can think of the branching, if you're modeling the branching problem as an MDP, then you can think of the branching problem as finding the optimal policy in this MDP. Whenever we talk about MDPs, we typically equate that with reinforcement learning. Unfortunately, as we'll see, there's a few important challenges in deploying RL and these for this particular problem. So the first one is exactly how do you represent the state? That's maybe slightly more general than pure RL, but you can imagine that there's sort of two levels of state representations. One will be the global level, including things like the original MILP, the tree, bounds, and which node you're in, stuff like that. And then the node level, which is going to include more local ideas such as variable bounds, the LP solution, and other type of simplex statistics. You can, of course, think that this tree that you're exploring will grow, right? So your state space, in a sense, does not come in a fixed size or a fixed length vector. And in addition, you'd like to be able to model problems of different sizes. So if you think of the coefficient matrix A that I talked about earlier, you'd like to be able to model things with, you'd like to be able to model problems of different sizes. So for that, we're going to use a graph neural network. And this was really the contribution of this work. If we go back to reinforcement learning, though, there are a few more challenges here. One is that how do you get episodes or trajectories? Well, what you need to do is you need to actually solve the MILP to get a trajectory. Okay, so if you're going to try to solve large MILPs, this can take a lot of time. This is especially true if your policy that you're using to solve the MILP is not very good. Okay, because it will lead to larger trees, and that usually takes more time. So what we do here is we're going to train on small instances, but we'll show later in the experimental result that thanks to the graph neural network, even though we train on small instances, we can actually generalize to larger instances of the same in the same family. Then, and perhaps foremost, the problem is one of a reward function, right? If you're going to build this RL agent, you need to specify a reward function. Here, there's no real consensus on what the reward should be. And so instead, what we do instead of trying to handcraft a reward function is we turn to the solvers and say, for each decision they make, each branching decision, they have a good expert, okay? And so the expert may be myopic, but it's still a very good expert. And so instead of deploying a full RL system, we think of it like an imitation learning problem, okay? So I'll explain that a little bit later on in more details. Of course, I should say that there's been lots of machine learning approaches that do similar things for node selection, for variable selection, which is what we care about, but also for cut selection and primal heuristic selection. These, I must say, were all from all sort of predate this work, so pre-2020. And at the end of my conclusion talk, I will highlight a few more recent work. And of course, Vinod's talk from this morning is a prime example of such work. Okay. So now let's see how we can exactly model this system. So the first thing is, how would we model a MILP? Okay, so it's not like it comes with a simple vector that you can model with a neural network, but I guess one key observation here is that the MILP has a natural representation as a bipartite graph, where in one of these partitions, you have the variables. So this would correspond to a MILP with 3 variables. And then on the other side, in the other partition, you have the constraints. So this would correspond to a MILP with 2 constraints. And then the edges denote non-zero coefficients in A. Okay, so basically, if a variable V0 is under constraint C0, then there's an edge in between these two. Of course, the features associated with each of these nodes will change over time, but the graph structure will be fixed through time, right? Through your exploration or your exploration of solutions in this space. Then there's this question of, okay, so how can you model this graph with the neural network? Well, we turn our attention, or I sort of introduce this idea here of using graphical convolutional neural networks. You may recall Vinod are also using that. The basic idea here is that we take this graph, which represents our MILP, as input. We process it through this GCNN, and then the GCNN predicts which action to take. Okay, so the output of the GCNN is effectively a policy. Based on the states, it gives you a distribution over actions. The advantage of GCNNs, or graph neural networks in general, is that they're permutation invariant, which is useful here because there's no natural ordering of these variables and constraints. And also their computation will scale with respect to sparsity, which is good because here often the A matrix is quite sparse. Okay, maybe I'll go into a little bit more details. Actually, if there are questions, I can go back to this slide. This really tells you a little bit more about the depth of these GCNNs that we've trained, and also how do we count for the fact that the graph is bipartite. Okay, so
let you know that you have about 6 minutes.
6 minutes, perfect. Thank you very much. Okay, so empirical study, some results. So first, because we are training things using imitation learning, we need an expert. For the expert, we chose to pick full Schwann branching, which is a really good branching rule, right? So if we could imitate it, that would be great, but it's also very expensive. So if we could imitate it with a fast neural net, that could lead to interesting improvements. And what we do is behavioral cloning. So effectively, we take instances of MILPs that we want to solve, we run them through the solvers using FSB, and we record all the decisions of the solvers as well as the state. Okay, so our data set is effectively, we have pairs of state and actions. Okay, so the big advantage of doing this is, as I said earlier, there's no reward function. It's supervised, and really we're framing this as a supervised learning problem, although of course these examples are not IID. The main disadvantage is that whereas RL policies could theoretically learn something optimal, here we're going to be bounded up, right? The quality of our decisions, they cannot be better than the full strong bench. And we are going to implement this in the open source solver skip. Okay, I should also say using machine learning for imitation learning is not new. And in fact, we can compare it to some of these approaches in terms of accuracy. So this is a first problem we looked at called minimum set covering. And we're simply comparing the accuracy of GCNNs compared to other machine learning models. Some of them use ranking approaches at predicting the variable that full strong branching this picked for predicting basically the scores of full strong branching. And so that's why we have accuracy at 1, accuracy at 5, and accuracy at 10. Of course, this is sort of reassuring, but at the end of the day, what we want is we want to be able to see if machine learning can actually, if this GCNN, for example, can actually help the solvers, right, for the downstream task of solving the problem, not just for predicting which variables to branch on. So this is still for minimum set covering, and there's really 3 sets of results here. First, we're comparing GCNNs to full strong branching and the reliability pseudo-cost branching, which I talked about earlier, on a set of easy instances of the minimum set covering problem. These had 500 rows and 1,000 columns. And these were actually the type of problem or distribution of problems we trained with. And then so some of the results here are that, at least in terms of time, we tend to be a little bit faster than reliability pseudo-cost. And of course, we're much faster than full strong branching, but this is to be expected. The trees we get, though, are definitely much bigger than the ones from full strong branching. There may be good reasons for that. What's also interesting here is, although we only train with easy instances, we can actually, the GCNNs allow us to generalize to much bigger instances. Okay, and in these bigger instances, again, we're doing fairly well. So it's paying off in the sense that we're doing better than Skip's default, which is the RPB, the reliability pseudo-cost, in terms of solving time, and we can also generalize to harder problems. I imagine I may only have a minute or 2 left, so I think I'll skip these 2 results. They're sort of in the same vein, where the GCNN is allowing us to outperform Skip and also generalize to harder instances. Okay, so some concluding thoughts. We've shown here that we can tune your BNB solver to a class of problems of interest automatically by using a GCNN for branching anyway. Of course, the issue with that, there's no guarantee outside of the training distribution, right? We show that we can generalize maybe the slightly harder instances in terms of size, but we don't think this would generalize to different instances, to a different family of instances, is what I mean. And of course, it requires training instances, right? Which works really well if you're solving a problem over and over again. If you've done that for a long time, you might have gotten historical data, but which may not work really well in all settings. So the paper was published at NeurIPS, not this one, but I guess the last one, 2019, sorry, and code is available. I also want to mention in finishing some more recent work. So there's recent work that uses some of the ideas but proposes a reinforcement learning approach. This does seem like a natural next step, although as far as I understand, we don't necessarily have a reliable reinforcement learning system that outperforms this sort of imitation learning setting everywhere. There's also interesting work by Didier Chitla and colleagues on looking and trying to explain some of the properties of GCNNs for combinatorial optimization. And I should also say that in all of these, whenever here we're comparing time, there's something that perhaps isn't absolutely fair. It is that the architecture, right, the computational architecture we're using isn't the same. In particular, this GCNN is being run on GPUs, whereas the default skip runs on the CPU. Okay, and so you could imagine that perhaps it's the the GPU that's getting the advantage. So there's recent work by Gupta and Gas and others associated with others in Montreal that have been able to port some of the GCN operations to the CPU and still see some of the advantages. The last thing I'll mention quickly is one of the struggle in these sorts of projects, I believe, is to obtain data, is to understand lots of the intricacies of some of these solvers. And some people in Montreal have been developing this framework called Ecole.ai, which is an API and benchmarks for MILP adaptive solving. And if you're here, Maxime Gas will actually talk about this framework later on today. So thank you very much for your kind attention, and happy to take questions.